me 1 or 2 minutes to do these things. Okay. Please somebody confirm in the chat box that whether you can see the slides or not. If you can see it, then I will start today's session. Okay. So there are many questions regarding enzyme kinetics in the last week that we were not able to finish. So we will start with those questions, and once we are done with that, we will move to week 5 lectures. Okay. So we finished till question number 15. So we will start from question 16 of week 4. So this is the first question of today's session. It states that given an enzyme with a Km equals to 10 millimolar and Vmax equals to 100 millimolar per minute and substrate concentration, that is S concentration, is 100 millimolar, which of the following will be true? Okay, so they have given us the values for Km, the value for Vmax and the substrate concentration. Now there are 4 options, out of which you have to choose the correct one. This is a very important question and a mathematical question. So I would request all of you to try to solve this question, and then obviously I will show you the answer. Okay. First, it will just take like 30 seconds or so. Please try it out by yourself. So this particular mathematics can be solved by your Michaelis-Menten equation. Just think about it and you will get the correct answer for that. Okay, I will give you like 30 to 40 seconds for all of you to solve that. Once you come up with the correct answer, you can write it in the chat box and then I will show you the correct answer. So what is our Michaelis-Menten equation? It is Km plus substrate concentration, where V0 is your initial velocity equals to Vmax, that is the maximum velocity, into substrate concentration divided by Km is our Michaelis-Menten constant, and again S is our substrate concentration. So this is the relation between velocity and substrate concentration, Km, etc. So this is your velocity. If any of you had got the correct answer, then you can write it. Okay. So let us see what will be the, okay, I can see one option. Yes, absolutely, you are correct. The correct answer for this question was option A. So let us look at the options one by one. So the first statement says, yes, again another answer, absolutely correct. The first option states that a 10-fold increase in Vmax would increase the velocity by 10-fold. So we can just look at the relation between V0, sorry, 1 second, just give me 1 second. So the relationship between V0, 1 second, the relationship between V0 and Vmax is just proportional. We can see it from this equation that V0 and Vmax are proportional to each other. Now, if we do increase the Vmax by 10 times, obviously the value of V0 would also increase by 10 times because they have a proportional relationship with each other. So our first option, that should be the correct one. Coming to the next option, still we already know the first one should be the correct. Let us look at the other options to understand why those were wrong. The second option states that a tenfold decrease in km would increase the velocity by tenfold. So where is our km? Here in the denominator. What is the relationship between velocity and km? Is there a direct relationship? There is not. We can see in the denominator there is Km plus substance concentration. That means V or V0 or velocity does not have a directly reciprocal or inverse relationship with Km. So we can't just simply tell that by increasing Km tenfold how V0 will be affected. We would not be able to tell that because there are no direct relationship. Okay, so our second option was wrong. The third option is again same. A tenfold increase in S would increase in velocity by tenfold. So we can see from the equation that the S or substrate concentration is here and here as well. So if we are increasing it by tenfold, so it will be like 10S in the upper portion and also 10S in the lower portion. And the relationship is not simple reciprocal. Okay, the relationship is complex. It is also in the numerator and also in the denominator. So again, they will not have a simple relationship where you can just increase one by tenfold and another one will also increase or decrease by tenfold. So this is also wrong. And the fourth option is a tenfold increase in Vmax would decrease the velocity by 20-fold. First of all, the word decrease is absolutely wrong because we already know that V0 and Vmax are proportional to each other. Okay, so if one increases, the another one will also get increase, and the relationship is very simple. It is directly proportional to it. So if we increase it by x amount, V0 will also increase by x amount. This is the simplest relationship. So that's why our correct option for this particular question was option A. Moving to question number 7. Okay. This states which of the following is not true for enzymes. The first statement is they increase the rate of the reaction by stabilizing the transition state. Okay, this is our first statement. The second statement is they lower the activation energy by altering the products of a reaction. This is our second statement. Third statement is they means enzymes, they only function when they are in intact cells. And the fourth statement is they make thermodynamically favorable reactions to proceed. They cannot make unfavorable reactions to occur. So these are the four statements. Now we have to understand which of these statements are true. Okay. If anybody can guess that, you can write it down in the chat box. Meanwhile, I will explain the statements one by one. So the first one states they increase the rate of the reaction by stabilizing the transition state. Okay. So let us see how does the reaction diagram look like. Okay, let me just remove it. Let me draw it again. Okay, that will be easier for you to understand. Suppose this is our substrate and this is your product. Okay, and it's come like this, and after you have added your enzyme, it will look something like this. So this particular thing has been changed due to the addition of enzymes. This is your delta G and this is your delta G dagger. So we all know this particular diagram for any kind of enzymatic catalytic reaction. So the first statement that states they increase the rate of the reaction by stabilizing the transition state. Absolutely yes, because what is the basic reaction? Say E plus S to ES, and from ES we are getting P. So this is our transition state. The work of enzyme is to decrease the activation energy that is required to get to this transition state. They basically lowers this activation energy. That's why more number of substrate molecules can now move from reactant side to the product side. So our statement 1 is the basic of the enzymatic catalysis reaction. The next statement says the lower the activation energy, sorry, yeah, 1 second, I just wrongly read the first statement, very sorry. Every time I am just explaining that it decreases the activation energy, but sorry, it is here written as they increase the rate of the reaction. So obviously this is a wrong one. I explained it, whatever I explained, that is the correct one. They are decreasing the activation energy that is required to get to the transition state. That is the correct statement. But in the first statement it is written they increase the rate of reaction by stabilizing the transition state. 1 second. There is a okay. The next statement says the lower the activation energy. I think there is a mistake of the question. Give me 1 second. It's written the second statement which is not true. Okay, again, just give me 1 second. So this means they are asking which of the options are false. Okay, I just got confused with the words, very sorry with it. Let me explain this particular question from the beginning. I just got confused what is written in the question. So in the question, the thing that was written, which of the following is not true, that is which of these statements are false. Actually that we needed to identify. So our false statements are 2 and 3. So the first statement that we are saying here, they increase the rate of the reaction by stabilizing the transition state. Yes, the transition state's energy is lowered. That means it is being stabilized. So our first option is true. That's why we will not take this option, because in the question it is asked to select the non-true options, that is the false option. So our first statement is true, so that's why we will not take the first statement as non-true. Okay, fine. Moving to the next statement, they says the lower the activation energy by altering the products of a reaction. No, nothing like that happens. If we look at the diagram again, we can see the substrate and the product are same. You are getting the same product. There is no alteration in the product formation. I mean the product is P itself. It is not changing into something else like P prime or P double prime. It is the product P itself, but the activation energy for the reaction has been lowered. So the next statement, which is saying that the enzymes alter the products of a reaction, is actually false statement. They does not alter the products of a reaction. So our second statement is false. Hence, in our question it was asked to identify the false one. So yes, 2 is a false statement. Moving to the next one, it states they only function when they are in intact cells. That is not the case at all. This means they can only function in vivo. Yes, enzyme does work in our body in vivo, but this enzyme also acts outside the cells as well, because that's how researchers do all the works with proteins. Basically, they use these enzymes many times, different types of enzymes to break the proteins, to hydrolyze, to do some kind of reaction or modifications of protein, and they work very finely most of the time. Of course, different type of condition will be required, reaction conditions, but most of the time this enzymatic catalytic reactions goes very well in our labs as well. So the third statement, that enzymes only function in intact cell, is a false statement. Obviously, in our question they are asking us to identify the false one. So third one is also our false statement. Coming to the fourth option, it states they make thermodynamically favorable reactions to proceed. They cannot make unfavorable reaction to occur. Again, this is the wrong statement, because there are many options. Catalyst, enzyme is basically a catalyst. Catalysts are known for this, that obviously if a reaction is thermodynamically favorable, they can do it in a less time, that is, they are increasing the rate of the reaction. But many times, because they are able to decrease, or they are able to stabilize the transition state, in many cases they are prone to activate, or they are prone to catalyze the thermodynamically unfavorable reactions as well. Okay, so this is our true statement. Fine. So according to the question, we have to select only the false one. So our option 2 and option 3 was the false statement. So the correct option for this question is option C, where we state 2 and 3 are the false option. Other options 1 and 4 were true statements. Okay, I made a mistake about this word, so very sorry for that. Okay, let us look at the next question, question number 18. It states enzyme X exhibits maximum catalytic activity at pH 6.5. Okay, X shows a fairly sharp decrease in its activity when the pH goes much lower than 6. Again, fine. What could be the likely interpretation of this pH activity? So there is some enzyme X, we don't know, but it have its maximum activity at pH 6.5. Whenever you lower the pH below 6, its activity gets hampered. So what can we say from this? There are 4 options. What can we choose? I will give you like 10 to 15 seconds to consider the options. The first option is a glutamic residue is there on the enzyme which is involved in the reaction. That is, a glutamic residue is on the catalytic side of the enzyme. A histidine residue is on the catalytic side of the enzyme that is involved in the reaction. That is your second option. The third option is the enzyme has a metallic cofactor, and the fourth option is the reaction relies on specific acid-base catalysis. So choose your option and then I will show. You should already guess. Okay. Yes, absolutely. The correct option is option B. Obviously, from the statement we can understand that as the activity of this enzyme is highly dependent on the pH, then in its catalytic side there remains some kind of amino acid residue which is pH active. Suppose we say the side chain is pH active and the pH is kind of neutral, not entirely not very strongly acidic, not very strongly basic, kind of in the middle, not neutral exactly, but kind of in the middle, slightly acidic region. So first option is a glutamic. We all know that glutamic acid, this is highly uh, glutamic acid means you have your COOH groups. So the pH values, if you look here, sorry, one second. Huh. If you look here, you can see the values or the pK values for all the groups in case of glutamic acid. The COOH group especially are very low. Alpha COOH has a pK value around 2.19 and the side chain has a pK value 4.25. So obviously also its pI also falls in the region of acidic pH region. So glutamic acid will not be something that will act in the neutral kind of pH region. But if we look for histidine residue, if you look here, the side chain pK value for histidine is 6. Okay. So obviously from that we can assume at 6.5 it does have a very high activity. But as soon as you get the pH value less than 6, that is the less than the pK value of its side chain, that means as soon as the pH gets less than pK, the histidine will start to protonate itself. The side chain of histidine will start getting protonated. This will again, that means there will be an additional charge. So you know this very well, for any enzyme to function, the catalytic site has to be very specific. But in case of histidine, as soon as you move from its side chains pK and lower the pH less than 6 and it gets protonated, it might happen that the protonation is somehow hampering the whole catalytic activity. It is hampering the substrate to come and bind with the enzymatic site, active site. So the most probable reason for this observation should be option B, considering the pK values of the side chains. Okay. The third option was unrelated fully. Metallic cofactor has nothing to do with the pH, and the reaction relies on specific acid-base catalysis. This is also not true. Not like any acid-base catalysis is going on. It's just the enzyme's active site that has a histidine residue, and you can see the effect of pH on it. Moving to the next one, it states a classical uncompetitive inhibitor is a compound that binds, and there are 4 options. So I am not going to ask all of you to answer this. I'll just quickly explain it. So we already know in case of reversible inhibition, there are mainly 3 kind of inhibition that can take place. One is competitive, one is non-competitive, and another one is uncompetitive. These are the 4 types of reversible inhibition that can take place. Now what is the case for uncompetitive inhibition? If we do look, this is our normal enzyme catalysis reaction. Fine. Now what happens in case of uncompetitive is that the inhibitor binds with the enzyme substrate complex to form a ternary species ESI. Now after it binds with the enzyme substrate complex and form this ternary species, this can no longer form any kind of product. So let us look at this is the basic reaction that follows by uncompetitive inhibition process. Now let us look at the options. The first one says it is irreversibly bound to the enzyme substrate complex, yielding an inactive complex. So now let us look here. Does the inhibitor binds irreversibly in case of this? Obviously this will be fully wrong, because first of all we are just discussing a part of reversible inhibition, a type of reversible inhibition. So obviously it will not bind it with the ES complex in a irreversible manner. It cannot, because in that case it would have been a irreversible inhibition. But from the very beginning, while classification, I said that this is a type of reversible inhibition. So our first option is wrong. Next one states it reversibly binds to the enzyme substrate complex, yielding an inactive ESI complex. Absolutely yes, it reversibly binds to the ES complex, forming a ESI complex which is inactive, which will not give you any product. This ESI complex can further go back because there is equilibrium sign and form this enzyme substrate complex again, but this ternary species will never lead to a product formation. Okay, so our second option, if you have any query, your voice is not clear, you can write in the chat box. I am reading it. Okay, if you have any query, please do write in the chat box. I am reading it and I will tell you the answer. Okay, so our second option was correct. The third option states the inhibitor reversibly binds to the enzyme substrate complex, giving an active ESI complex. This is the wrong place of the statement. Once the ESI complex has been formed, it is inactive because it cannot give you the product. So, here the statement that the ESI complex is an active complex is wrong. Be clear with one thing, ESI can break to form ES complex again. That is not the activity of the ESI complex. It is just staying in an equilibrium process with ES. Activity means whether the complex can lead to product formation or not. Because here you can see ES, this particular one, ES is our active complex which can lead to product formation. So, but when we look at ESI, it is an inactive one because it cannot lead to product formation. It does not have anything to do with this equilibrium. Whether it can give the product, that determines the activity. So our third option is incorrect as well. And the fourth one is the inhibitor irreversibly binds to the enzyme substrate complex, yielding an active ESI complex. The whole statement is wrong. First of all, it is stating the inhibitor binds irreversibly. That is wrong. I just explained in the first option. And then again it is stating the ESI complex is active, which is again wrong. So the only correct option for us was option B. Moving to the next one. It states an enzyme is assayed at an initial substrate concentration of 2 into 10 to the power minus 5 molar. Okay. So our initial, what do we have here? Our initial substrate concentration is 2 into 10 to the power minus 5. In 6 minutes, half of the substrate is used. So if you do remember the basic chemical kinetics, what do we define this time when half of the substrate is consumed? We call it T half. In what time half of your initial substrate is being consumed is called T half. So in this particular question, the T half is 6 minutes. Then it states the Km for the substrate is 2 into 10 to the power 3 molar. So we have our Km value as well. What will be the value for K in minute? What will be the value for the rate constant of the reaction in minutes? So these are your options. I will give you some time, like this will just take like 30 to 40 seconds to solve. Do solve and write down your answer in the chat box, and then I will show you how to solve it. Okay. Once any of you get the correct answer, do write it in the chat box. Anybody? Okay, fine. Let me show you the solution then. Okay. So first of all, let me write down the Km value again here. Km is 2 into 10 to the power minus 3. Fine. Now let us remember the how the curve for enzyme kinetics looks normally. So here is our velocity, here is our substrate concentration, and our enzyme kinetic curve looks something like this. We already know this. And this is your Vmax. And what is the value for Km? Km is nothing but a substrate concentration where the velocity is Vmax by 2. That is your Km value. So this is your Vmax. Fine. So Vmax by 2 would be someone around here, and this should be your Km value. We all know this from the Michaelis-Menten equation. We all know this particular graph and everything. So now see, the value for Km is 2 into 10 to the power minus 3 molar. Okay, I have not written down the units. This is 2 into 10 to the power minus 3 molar. Fine. So this particular substrate concentration is 2 into 10 to the power minus 3 molar. Now look at the initial substrate concentration that is given. The initial substrate concentration is 2 into 10 to the power minus 5 molar. We have already written it down here. The initial substrate concentration is 2 into 10 to the power minus 5 molar. That is very less than the Km value here. And what happens whenever the substrate concentration is very low than the Km value? Let us look at the equation. So our equation is Vmax substrate concentration Km plus S. If our substrate concentration is very less compared to Km, then we can just ignore this. If this one is very greater, we can simply ignore this. So our equation does become something like this: Vmax Km into S. Because this is very small, so adding a very small value to a large value can be ignored in general. So now look at the equation at very low concentration or low substrate concentration, the dependency of velocity and S. What is the relation? V is directly related to substrate concentration to the power 1, right? That means at very low concentration our reaction is first order. We have also learned this in our lectures as well, that at very low concentration our reaction remains first order, and at high substrate concentration it becomes zero order. So now we know that at lower substrate concentration our equation or our ongoing catalysis enzyme catalysis reaction is of first order. So now here let me write it. So now we have derived, or we can understand by looking at the S0 and Km value, that our reaction that is happening is of first order. Now we have to determine the rate constant of the reaction. What another value you have? You have the value for T half. Then what is the equation from chemical kinetics? If you do remember, T half is 0.693 divided by K, where K is the rate constant of the reaction for first order equations. Okay, first order kinetics, T half is defined as 0.693 by K. And we have already come to the conclusion that this particular reaction is first order. So, next step what we simply need to do, K will be 0.693 divided by T half. So, we already know our T half value is 6 minutes. So, just by dividing it, you can get the value for K is, I think, 0.115 minute inverse. Okay. So, this was not a difficult question at all. Just you need to understand the question or look at the values. Once you understood by looking at the values, okay, my S0 value is very less than Km, the substrate concentration is very low, you will quickly understand that at low substrate concentration the reaction becomes first order. And whenever you understand that, you just need to do it, you are just required to do a simple calculation like T half equals to 0.693 by K. That was all required to solve this question. But the wordings of these questions were a bit tricky, where you needed to understand that what has been said. The concept is basically checked in this question, not exactly mathematics, but the what kind of concept do you have in enzyme kinetics, that was being checked in this question. Hope this one was clear. Yes, someone answered the question yes as well. Yes, absolutely, you are correct. For the last question, the option A was correct. Moving to the next question. It states, Michaels and Mentane assume that the overall reaction for an enzyme catalysis reaction could be written as this. We already know this. I think one part of this is missing. This will be E plus S. Okay. Using this reaction, the rate of breakdown of enzyme substrate complex can be described by which equation out of the four? So what are they asking? Rate of breakdown of enzyme substrate complex. Who is our enzyme substrate complex? Just there is a wrong thing, just forget this. So this is our enzyme substrate complex. Now you have to describe its equation or expression of breakdown of ES. So breakdown of ES, how is ES breaking? Let us see. So basically you have to determine minus DES dt. Okay. So one breakdown is happening via this step, where it is in equilibrium with enzyme and substrate. So ES can break down to individual enzyme and substrate. This is your one step that can happen for breakdown. So the first thing for breakdown, we can write K minus 1 into ES. ES is breaking down to E plus S. Now if you look at it, ES is breaking down and the rate constant for this process is K minus 1. So again it will be K minus 1 into ES. Another step by which ES is breaking is this one, where it is forming E and the product, and the rate constant for this is K2. So the next one should be K2 into ES. This is another process by which it is breaking. So the correct answer, that by which expression you can describe the breakdown of enzyme substrate complex, is option number B, K minus 1 into ES plus K2 into ES. You just need to be very careful about what they are asking about. They are asking about breakdown of the complex. If perhaps they were asking about the formation of the complex, then you can see the ES complex is only been formed by one process, that is this step, the first step only. So in that case the reaction expression would be K1 into E into S only. So this is the all thing. Every time they say any kind of to write down any kind of expression, you just have to look carefully for the word, whether they are asking for the formation expression or the breakdown expression, and then find out the steps, and then it will be very easy to write down the equation. Okay, moving to the next one. Yes, the answer was correct again for Akshara. Yes. So this is your next question, question number 22. It states, which of the following statement is true about the region of the graph below where substrate concentration is very less than Km? Okay. I am just correctly showing you the answer because just in the previous slides we have discussed this equation, that what will be happen when S is very less than Km. Again, let me just write it down. It is like V equals to V max into substrate concentration plus Km plus substrate concentration. And whenever S is very less than Km, you can simply ignore this part in the addition. So your equation becomes something like this. So at this condition, the initial velocity V is equal to the catalytic efficiency multiplied by free enzyme. Okay. Now again you have to remember the catalytic efficiency, that is Kcat. This is called catalytic efficiency. It is defined by Vmax divided by total enzyme concentration, because we know Vmax can be only achieved when the entire enzyme is used for the reaction. So for Kcat, or the turnover number, that is basically defined as this one, that is Vmax divided by Et, Kcat. Fine. Now if we substitute, we can write down Vmax is equal to Kcat into Et. So now if we substitute this particular equation into our Michaelis-Menten one, so V equals to Vmax. Now in place of Vmax we can place Kcat into total enzyme concentration. There is substrate concentration divided by Km. Now look at the second option. It says the initial rate constant is equal to the catalytic efficiency Kcat multiplied by the free enzyme. So this Kcat by Km, again you have to remember once again, catalytic efficiency is defined as, one second, just this is not working. Okay, fine. Catalytic efficiency is defined as Kcat divided by Km. This is your catalytic efficiency. So in our equation, let me write it down again. This is not working. Okay, again if you look at the equation, Kcat by Km Et into substrate concentration. So this is our catalytic efficiency. Find the first thing, catalytic efficiency multiplied by free enzyme, okay, and substrate concentration. This was our correct answer. So what you needed to do, you just needed to substitute the whole thing. First of all, you needed to remember how to substitute Vmax. That Vmax is related to Kcat by this equation. Let me just correct it a bit. I just forgot to put down the bracket. Okay. This is your kcat value, and you can replace Vmax by simply kcat into Et, and once you place this, you come to this particular equation where kcat by Km is defined by the catalytic efficiency of a reaction, and which is then multiplied by Et and S. So if you get that equation, you can just read the option. In the option B only, it states that the initial rate is equal to the catalytic efficiency multiplied by free enzyme and substrate concentration. That is what we are getting from this equation. So our correct option is option B. Okay. I hope this is clear. Moving to the next one. So it states, in the following diagram, which kind of inhibition is represented? So again, we can see this is your diagram. You have your enzyme substrate, which is giving your product and enzyme, and here is your inhibitor. Now what kind of inhibition is this? If you have to say, I hope all of you know. So please try to answer it. Just look at where the substrate is sitting on the enzyme and where the inhibitor is also sitting on the enzyme. Just look at that and you can understand what kind of inhibition is going on. So we already know that there are three types: competitive, uncompetitive, non-competitive, for reversible ones. And then there is another one, that is irreversible one. Now if we do look at this question, the very important thing is, first of all, the fourth option is wrong. Why so? Because in every place we can see that there is an equilibration sign, that the substrate can bind and can also reverse back. In case of inhibitor as well, the binding of inhibitor with the enzyme is happening in a reversible process. It can bind but then can again come back to free enzyme and free inhibitor. So the whole process is reversible. So our fourth option is automatically cut out. So the only options we are left with are the first three: competitive, uncompetitive, non-competitive. So to answer this particular question, you need a correct understanding of what difference is there between these three different types. What is the basic difference? Now coming to the first one, competitive. From the very name it suggests that the substrate and inhibitor, these are the two things that are going to sit on the enzyme, catalytic side of the enzyme. They are competing. Now from the name itself you can say, if you are competing with each other, suppose you must have a same goal, only then you can compete with each other. If you are desiring a particular same thing, only in that case you can compete with each other. If your goal is different, or if something that you want is different, then there is no competition. So from the very name we can tell, if this is the catalytic site of the enzyme, then substrate and inhibitor, in case of competitive inhibition, will try to sit at the exact site. So now look at the diagram, what is happening. This is our active site, one of the active site of our enzyme. The substrate wants to sit here and fits here. The inhibitor also sits here and fits here. They are competing for the same catalytic site on the enzyme. So what can we call them? They are competing. That means the process is competitive inhibition. So whenever you see the diagram, this kind of diagram, and see that substrate and inhibitor both are competing for the same catalytic site. Because even if you look at the shape of the substrate and inhibitor, you can see that although they are different, the shapes are different, yet they both of them will very nicely fit at the catalytic site. So whenever you see this scenario, this means your inhibition process is competitive. Both are going for the same side. So our correct option for this question was that this diagram represents competitive inhibition. Okay, moving to the next one. It states, which of the following best describe the assumptions made in steady state kinetics analysis? So what was our steady state kinetics? So again back to this equation, E plus is ES, and from A to E plus P. So there are three options that are given, three statements. The concentration of S is decreasing. Does this involve the steady state kinetic assumption? No. The total amount of enzyme decreases, obviously. Does this, first of all, at the end of the reaction you get the total amount of enzyme back again. Initially the total in free enzyme concentration in the mixture will be decreasing. Free enzyme, because it is reacting with substrate, the free enzyme concentration will decrease with time, but obviously the total enzyme concentration will remain same throughout the reaction. The only statement here is the concentration of ES is constant. Now while the derivation of Michaelis-Menten equation, we did a steady state assumption which was d ES dt equal to 0, which means the rate of formation of ES is equal to the rate of breakdown or dissociation of ES. So that is the basic assumption that you can take any kind of steady state kinetics. So which of the statement is correct for this? If rate of formation of ES is same with the rate of dissociation of it, then at any particular time the concentration of ES will remain constant, that is with time ds dt equals to 0. That means with time there is no change in the concentration of ES. That was our steady state assumption. So the correct option for question number 2 is option C, that the steady state kinetic assumption was dES dt equals to 0, that is concentration of enzyme substrate complex is constant throughout the reaction. Moving to the next one, it states the number of substrate molecules converted to product in a given unit of time by a single enzyme molecule at saturation is referred to as what? I am just directly showing you the answer because a similar question we have discussed in the last session. So number of, in the last session I have explained this question in detail, so I am not going to do that again here. The substrate molecules converted to product per time per catalytic site of enzyme is the definition of turnover number for enzyme, and that is what asked in this question. So let us move to here. Yes, fine. It states, the question number 26 states, the double reciprocal form of the Michaelis-Menten equation, also called the Lineweaver-Burke plot, is given by this particular equation. To determine Km for a double reciprocal plot, what would you do? So this is the equation that you use to plot double reciprocal plot. Now how can you get Km value from the plot? Fine. Okay. So first option states you can multiply the reciprocal of the x-axis of intercept by -1, multiply the reciprocal of y-axis intercept by -1, take the reciprocal of y-axis intercept, take the x-axis intercept where v0 equal to vmax by 2. Okay, these are the four options. So first of all, you need to actually draw the double reciprocal plot. Fine. So let us just draw that. What is our double reciprocal plot? It looks something like this, where you plot 1 by V versus 1 by substrate concentration. And then you can get a plot like this. This is your y-axis, this is your x-axis. And this particular intercept is known as 1 by Vmax and the slope is Km by Vmax. And another thing is, here the x-axis intercept is minus 1 by Km. So this is the, one second, this is the normal double reciprocal plot. Now you have to determine the Km. Let us look at the first option. Multiply the reciprocal of the x-axis intercept by -1. So let us look at what is there. Here is the intercept at the x-axis is -1 by Km. In case of double reciprocal plot, the x-axis intercept is -1 by Km. Now they are saying in the first option that multiply the reciprocal of the x-axis. So reciprocal of the x-axis will be minus Km, because the intercept is minus Km. So the reciprocal will be minus Km, and then you multiply it by -1. So that will give you the value for Km. Exactly, we can get the value from for Km by this way. So yes, at the very beginning our option number A was correct, which was stating that from the x-axis intercept, by doing the reciprocal and then by multiplying it with -1, we can get the Km. Let us still look at the other option. The second option state multiply the reciprocal of the y-axis intercept. What is our y-axis intercept? It is 1 by Vmax. Can we anyway get Km value from that? No. If we do the reciprocal of this, 1 by Vmax will be, the reciprocal would be Vmax, and if you multiply by -1, it will be minus Vmax. It will never give you the value for Km. So obviously this option was incorrect. Take the reciprocal of y-axis intercept. Y-axis intercept again is 1 by Vmax and the reciprocal of it will be Vmax. This will not give you the Km value. So again the third option is incorrect, and the final option is take the x-axis intercept where V0 is equal to half Vmax. This option has been put here very trickily, because if you do remember the normal definition for Km, that is Km is basically a substrate concentration where V is equal to Vmax by 2. This is the definition that you read all the time for Km. But do remember that this particular thing that I am discussing, the substrate concentration or everything, that is valid for the V versus S plot, that the normal Michaelis-Menten equation, where you can get Vmax and at Vmax divided by 2, this gives you Km. This is not applicable for Lineweaver plot or double reciprocal plot. For Michaelis-Menten plot, normal V versus S plot, this option could have been correct. But for Lineweaver plot or double reciprocal plot, this is incorrect. So if somehow, if just by the definition you have selected the this option, then you would be wrong. So you have to be very careful what plot they are talking about. Okay. So our fourth option is not valid for double reciprocal plot. So it was wrong again. So the only correct option was option A. Moving to the next one. Okay. It states, it is a mathematical question again. It states, an enzyme catalyzes a reaction at a velocity of 20 micromolar per minute. Okay. When the concentration of the substrate is 0.01 molar and Km for this substrate is 1 into 10 to the power minus 5 molar. Assuming the Michaelis-Menten kinetics is being followed, what would be the reaction velocity when the concentration of substrate is A 1 into 10 to the power 5, 10 to the power minus 5 and B is 1 into 10 to the power minus 6. So what values do we have? So let us just write the equation first. So we have our first equation. Sorry, let me write down here. V max is 0 or Km plus S. This is your normal Michaelis-Menten equation. Now let me show you the answer directly. First of all, if you see, initially substrate concentration is 0.01 molar. Okay, let me write it down. Our substrate concentration was 0.01 molar, whereas our Km value was 10 to the power minus 5 molar. So our substrate concentration is very high than the Km value. So what will happen whenever our substrate concentration is very high? Now look at this equation. If our S is very high than Km, we can then simply neglect this part from the addition. If we just remove this from the addition because it is too small, now these things can cut, which will eventually give us V0 equals to Vmax. That is happens whenever the substrate concentration is very high, the reaction becomes zero order with respect to substrate. That is, it does not depend on the substrate concentration anymore. So what is the value of Vmax? That becomes the value for our V0 as well. So now we know the value for V0. Okay. Value for V0 in the reaction at a velocity, yes, already it is given 20 micromolar per minute. So you already know that, sorry, one second. Okay, so you already know that our VMB max value or V0 value, that would be 20 micromolar per minute. That is we are getting from the equation that I have shown here. Now let us look at the first option. What if we change our substrate concentration to 10 to the power minus 5 molar? So now for option A, our substrate concentration is 10 to the power minus 5. Now let us go back to this equation again. Let me write down the equation here again. V0 equal to V max is S plus Km. And our value for Km was again 1 into 10 to the power minus 5 molar. So for the first option, that is first math, that is A, both the value for S and Km are same. That means for the first case, Km equals to S. What will happen to the Michaelis-Menten equation if Km equals to S? Let us go back to this particular equation. Now we are saying Km and S are same. So now our equation will, become V max. We can write down S. Here is S, and instead of Km, again here also we can write S, because both of their values are same for option A, I mean the mathematics A. So now our V0 would be V max 2S into S. So if you cut it, so V0 is V max by 2. This is the exact derivation. Whenever the substrate concentration is equals to Km, your velocity becomes V max divided by 2. And initially we already know that our V max value is 20 micromolar per minute. So if you place 20 in place of V max, so your V will come 10 micromolar per minute. That is the exact definition for Km, as well as I have shown you all the derivations as well. Okay. So for option A, when S and Km are same, our V0 or initial velocity is Vmax by 2. We already know the value for Vmax for this particular scenario, and thus we already can get our V0 value. Moving to the next one, when substrate concentration is 10 to the power minus 6 molar. Now, as the substrate concentration is 10 to the power minus 6, it is almost comparable with the Km value. Your value for Km is 10 to the power minus 5 and your substrate concentration is 10 to the power minus 6. So, you cannot ignore any of them. It's just a 10 to the power minus 1 difference. Just a small 10 times difference, not a very huge difference, right? So you cannot ignore any of the part in case of Michaelis-Menten equation. So you have to use the whole equation in this particular case. So this is our Michaelis-Menten equation. So for mathematics B, the substrate concentration is 10 to the power minus 6. So for substrate, we are putting 10 to the power minus 6. Here also we are putting 10 to the power minus 6. Km value already we know 10 to the power minus 5. And Vmax value, at the very beginning we have determined that the V0 value at that concentration was Vmax, which we ended up that Vmax value is 20 micromolar per minute. So in place of Vmax, we can put 20 micromolar per minute. Everything is given, and when you solve it, you get a V0 value like 1.8 micromolar per minute. So if anybody does not understand any part of this math, please do tell me. I will describe this once again. But you have to be very clear that you understand that how to solve these questions, because it might be more difficult in your exam or in the assignments. So if anybody has any doubt that how we are solving this particular mathematics, then you can ask me again. I will tell you. Otherwise, if all of you have understood, then that is very good. Okay. So till now I don't see any response in the chat box, so I can assume that all of you have understood that how to solve this. Okay, then let us move to the next question. It states, for a reaction that can take place with or without catalysis by an enzyme, that what would be the effect of the enzyme on the standard free energy change activation energy of the reaction and initial velocity of the reaction. So what is the question basically stating? There is a reaction that can take place without the catalysis, without the catalyst itself. Okay, so you don't need the enzyme to act upon to have this reaction. In this scenario, what will be the effect if you still add the enzyme? So essentially you do not need enzyme, but still you are adding. So what will be the effect of the enzyme in the standard free energy, activation energy and initial velocity of the reaction? Now let us go back to the very first thing that we learned in case of enzyme kinetics. So this is your energy coordinate and this is your reaction coordinate. Okay. So the first statement that it state that the reaction can take place without the catalyst as well. That means it is a thermodynamically favorable reaction. For any reaction to be thermodynamically favorable, what is our criteria? That delta G must be negative. What is the delta G if you look here? So this is your, one second, this is your substrate, this is your product, and the difference between the two energy is known as the delta G. Now we can see the product lies below. So whenever you will subtract the value, you will get a negative one. So the reaction will be thermodynamically favorable. This is your delta G. Now we are adding this is without any enzyme. Now you are adding the enzyme. What happens when you add the enzyme? The reaction curve, the reaction curve looks something like this. This is your ES complex, if I suppose, or the transition state. So we can clearly see, one second. So we can clearly see that there is a decrease in the delta G double dagger, which is known as the activation energy that is required to reach the transition state. Now you need to be very clear that the delta G dagger that I am showing here and the delta G that I am showing here are completely two different parameters. The delta G here I am showing, it is a thermodynamic parameter. It only depends on the energies that the substrate and product is standing. So if it is our energy coordinate in the y-axis and if it is our reaction coordinate in the x-axis, then there is no change ultimately in the energy values in presence of enzyme or in absence of enzyme. The delta G value remains same in both the cases. So delta G is purely a thermodynamic parameter which does not deal with the rate of the reactions in any way or kinetics of the reaction in any way. But we all know enzyme is something that deals with the kinetics of a reaction itself. So it will not interfere with the thermodynamic parameter. It can only affect the rate of the reaction, but it cannot interfere with any thermodynamic parameter of a reaction. So whenever you are adding an enzyme, there is ultimately no change in the standard free energy, that is delta G, which is a thermodynamic quantity. It does not matter whether you add an enzyme or not, it would not change. So our first option, that what would happen for standard free energy, is it will remain unchanged. So now look at the options. We already know one will be unchanged. So obviously these two options are automatically we can omit. So these two options are still in play. Let us look at the next statement, option 2. Activation energy of the reaction. So what happens whenever you act an enzyme? Your delta G double dagger, which is a kinetic parameter, that decreases. That means the activation energy that you require to reach to the transition state has been decreased. We all know that catalyst decreases the activation energy that is required. So the second option 2 should be decreased. So we already know what option should be the correct one. 1 has no change, 2 decreases. The third option is initial velocity of the reaction. So obviously if the activation energy barrier is been lowered, so more number of substrate can go from substrate to product formation. So our initial velocity for the reaction or the rate of the reaction would be increased. So the first option was correct. Delta G will not change. Activation energy or delta G double daggered would decrease and initial velocity of the reaction would increase. Okay. Moving to the next one, it states a small molecule that decreases the activity of an enzyme by binding to a site other than the catalytic site. What it is termed as? So basically they are allosteric inhibitors. I think in week 5, I think so. Let me look at the material. I think week 5 has dealt with allosteric inhibition, not before that. Anyway, so any kind of small molecule that decreases the activity of the enzyme but does not bind at the catalytic site. So generally what it does, suppose this was your enzyme, this was your catalytic site. Let me draw another site here. Just let me draw another side here. So just let me draw it again. 1 second. Suppose your enzyme looks something like that and your substrate looks something like that, that can fit into this catalytic cavity. This is your catalytic cavity. But a small molecule that can bind to the some other site that is different from the catalytic site, then it will basically induce a change in the enzyme and the enzyme will start to suppose look something like this, and the substrate can no longer fit in the catalytic site. If the substrate can no longer fit at the catalytic site, that means the rate there will be a decrease in the enzymatic activity. So these kind of small molecules are known as allosteric inhibitor. Okay, small molecule inhibitions. Fine. Which induces a change in the catalytic site of the enzyme. Moving to next one. Okay, I think this is a very easy question. I just quickly read it. This question states the underlying reaction shows a metabolic pathway. So W is forming X via enzyme A, X is converted to Y via enzyme B, and Y is again being converted to Z via enzyme C. What would happen to the rate of production of Z if the concentration of enzyme A was increased, but the concentration of enzyme B and C remain constant? What would happen? Simply say I have increased the concentration of enzyme A. So now the amount of X has been increased in our reaction mixture because there are more number of A molecules. So more number of W molecules can come here and getting converted. So the rate of the reaction has been enhanced. But if you look at the other step, For the next step to happen, suppose here is our enzyme B. Now the number of X molecules has increased, but you have not changed the concentration of enzyme B. So one enzyme B will still can react with one X molecule. No matter how much the substrate concentration has been increased for enzyme B, it cannot act upon all of them because the catalytic site for enzyme B is fixed. The substrate concentration for it is very high, but the rate is not dependent on the substrate concentration in that case, because it does not have more place to accommodate. Unless you increase the enzyme concentration, the rate of this transfer is not going to hamper, because you already know whenever the substrate concentration becomes very high, in that particular scenario, the reaction generally becomes zero order with respect to substrate. That is, there is no further effect of substrate concentration on the rate of the reaction. It is already doing the best it can do. It cannot accommodate more substrate molecules even if you keep increasing the substrate concentration. So basically, although enzyme A is now quickly producing X molecules, but since the number of catalytic site for the enzyme B has not been increased because the concentration is same, so this particular reactions rate is independent of the concentration of X or substrate of this particular reaction. So there will be no change in the rate for this second reaction, consecutive reaction. And obviously for the third one as well, because there is no change in the formation of Y, the rate of formation of Y. So again there will be no effect on rate of formation of Z as well, because enzyme C concentration is also staying same. So again the whole process or the whole rate process will be same for them. So the correct option for question number 30 was option A. Okay, these are very important question. It states a reversible non-competitive inhibitor binds reversibly at a site other than the active site. This binding leads to what? It increases the Km and Vmax remain constant. It increases in Vmax and Km remains constant, decrease in Vmax and Km remains constant, and no change in Vx and Km. From which plot you can say that? First of all, this is competitive inhibition. So if we just draw the Michaelis-Menten plot, non-competitive inhibition. What happens in case of non-competitive inhibition? The equation if we write, this is your normal enzyme kinetics. Now in case of non-competitive inhibition, the inhibitor can bind with the inhibitor can bind with the enzyme itself. The inhibitor can bind with the ES complex as well. Okay. This can also interact with the substrate to form ESI. So ultimately, both this EI and ESI are unable to give you any product. Only the enzymes which are binding with substrate will be able to give you the product. Okay, so this is our binding mechanism for non-competitive inhibitors, that they bind both with the free enzyme and the enzyme substrate complex. So let us go back to the Michaelis-Menten curve. So this is a curve look like from without inhibitor. This is what it looks like. Now you are adding non-competitive inhibitor in your system. What will happen? Because if you look at this particular mechanism, first of all the enzymes are unable to react with the substrate because some are forming EI. Again, some enzyme substrate complex are also forming ESI. So, the effective formation of the product is being hampered. All of the enzymes are unable to interact with the substrate and give product. So, the initial velocity should be less. Now, what would happen to the final velocity? This is your Vmax. What should happen to the final velocity? Now, if you look at this mechanism again, yes, you can see the total enzyme concentration is never available to the substrate. Even if the substrate interacts with the enzyme, the inhibitor can still come and deactivate this enzyme substrate complex and no longer give you the product. Yeah, in the competitive case, the case was something like that once the substrate is forming ES, the inhibitor cannot do anything. The ES will lead to the product formation. But in case of non-competitive, even if the enzyme and substrate has formed the enzyme substrate complex, the inhibitor can still react or still interact with the ES complex and make it inactive. So ultimately, the total enzyme concentration is never going to be available as free in the system. So if it's total enzyme you cannot use in your system, then you will never be able to achieve the same Vmax without inhibitor that was there. You can never be able to achieve that same maximum velocity because your total enzyme is not available to you. So what happens? That means that means the curve looks something like this, where there is a initial velocity decrease and also Vmax has been decreased. Next is, this was the normal Michaelis-Menten plot. Now let us look at the Line-Weber plot or double reciprocal plot. So what do we plot in this case? We plot 1 by V versus 1 by substrate concentration, and without inhibitor we get a line like this where the intercept here is 1 by Vmax and the intercept here is minus 1 by Km. Now what will happen in case the Vmax has been decreased? Fine. But if we look at the Km value, let me go back here. What is the Km value? So without inhibitor, this is our without inhibitor, this is with our plus inhibitor. So without inhibitor, this was our Vmax. So Km is some substrate concentration where V equals to Vmax by 2. So half of Vmax will be here. So suppose this is here. Let us look at the corresponding substrate concentration. This was Km value without any inhibitor. Now let us see what will happen to the after addition of inhibitor. Now this is after adding inhibitor. This is our Vmax. Something like this. So half of it will be around this. So again move to this curve. Our Km is coming here. So the value for Km is same in presence and absence of inhibitor. You can yourself draw and look at that. The Km value is same for both the cases. Now let us go back to the Line-Weber plot. So we already know our Km does not change. So the slope of our x-axis, which is basically minus 1 by Km, is not going to change. Km is same, so the slope is not going to change. But we already know that the Vmax would decrease. The value of Vmax has decreased. So the slope's value 1 by Vmax will obviously increase. So it will look something like this. So this is your 1 by Vmax prime in presence of inhibitor, and obviously the overall velocity has decreased, so 1 by V is above the non-inhibited straight line. So from this what we get, the Km value does not change, but the Vx value, Vmax value decreases. So now let us look at the option. The only option that states it is option C, that there is a decrease in Vmax value but the Km remains constant. Okay. Hoping this one is clear. Moving to the next one. A non-competitive inhibitor of an enzyme catalyzed reaction. Just in the previous slide I have discussed. Yes, it does decrease the Vmax value. We just discussed it. It is the correct thing. Binds to Michaelis complex or ES complex. Yes, non-competitive inhibitors can bind to ES complex forming a ternary one, that is ESI. So this one is again correct. Can actually increase reaction velocity in rare case. No, we have already seen, because the enzyme is not available because of the formation of EI and ESI. So that's why the velocity gets decreased. It is never going to increase in case of non-competitive inhibition. So the only correct statements were actually 1 and 2. So our correct option is option C, that 1 or 2 are true for non-competitive inhibition. Moving to the next one. It states, in a Lineweaver-Burke plot, a competitive inhibitor shows which of the following effects. First statement says it moves the entire curve to the right. Second statement says it moves the entire curve to left. Third statement is it has no effect on the slope. And the fourth statement is it changes the x-intercept. Now let us look the scenario for competitive inhibitor. First of all, the mechanism. Again, I have write it down. In case of competitive inhibitor, the good thing is the enzyme only competes for the enzyme's catalytic site. It does not go to bind with the ES complex. It only binds the catalytic site of the enzyme in a reversible manner to form EI, which will not lead to a product, but it can again break down to give you the free enzyme. So this is your mechanism. So how does it look like? So basically, if you have this site for enzyme, suppose this is your substrate and suppose this is your, sorry, my drawing is bad, and suppose this is your inhibitor. So both of them are competing for the catalytic site here. Now if we plot V versus S, how does the plot looks? For normally it does look like that. V versus substrate concentration, Michaelis-Menten normal plot. Now for competitive inhibition, what do you know? That initially, if inhibitor is blocking the sites or catalytic sites of the enzyme, then substrate can no longer bind to it. This is a very good thing for competitive inhibition, that either substrate will bind or inhibitor will bind. They will not bind the enzyme together. Either one of them is going to bind. Now if the inhibitor is going to take the place, then the substrate can no longer come here. That means the overall rate of this reaction will decrease initially, because the substrate is not getting the entire active sites of the enzyme. Some are already blocked by the inhibitor. So what will happen to the curve in that case? This is your without inhibitor, and now what will happen? So the initial velocity will get decreased. Why? Because the enzyme sites are not fully available to the substrate. This is at low substrate concentration. You have to remember, at x-axis we are plotting substrate concentration. At low substrate concentration this is happening. Now what will happen if you increase the substrate concentration too much? That is at very high substrate concentration. Now as I just said, for the enzyme, both are competing to sit in the same place. It's like musical chair. Both of them, say suppose one member is from S team, another member is from I team. They are fighting with each other for the same place. Now, if somehow I suddenly increase the number of S molecules in the reaction, that is, I have increased the overall substrate concentration. In that case, what will happen? Now, as substrates are much higher in number than inhibitor, obviously by probability, more number of S will be able to sit in this place compared to inhibitor, because now enzyme sees that there are more substrate molecules around me than the inhibitor molecules. So eventually, if you increase the concentration too much, ultimately the inhibitors will fail in the competition to bind or sit in that catalytic site, and the substrates will eventually win. So your overall enzyme concentration will be equal to the free enzyme concentration that you initially put in the reaction. So now if your whole enzyme concentration is available to you, so Vmax will be achieved again, because Vmax only depends on the free total concentration of enzyme in the reaction. And now if you can achieve that at higher substrate concentration, Vmax can be easily achieved as well. So our curve will look something like this. Initially there was a decrease because of the binding and forming EI, but eventually with increase in S concentration, the Vmax will be reached. This is the line for plus I, or with competitive inhibitor. Now let us look, this is our Vmax. Without inhibitor, the Km value, what was the Km value? So if this is Vmax, this is Vmax by 2. So for this without inhibitor, our Km value is this. What will happen for this? Again for with inhibitor, the Vmax is same. So Vmax by 2 is also same. Now let us look at that. For this curve, the Km value is coming as here. So for competitive inhibition, the Km value increases. We can clearly see it from the graph that it increases. Now what will happen to the Lineweaver-Burke plot? That is being asked in the question. So let us plot that again. So this is your Lineweaver-Burke plot. You plot 1 by V versus 1 by S. This is your 1 by Vmax, and this is your minus 1 by Km. Now already we have seen from Michaelis-Menten curve that the Vmax doesn't change. What is the Vmax here? 1 by Vmax your slope. So the slope doesn't change. But what does change? The Km value increases. So obviously here what will happen? If Km is high, 1 by Km will decrease, but the slope is remaining constant because Vmax is same, so the slope is same, but the Km value has decreased. So minus inhibitor was this, but with inhibitor, in case of competitive inhibition, the curve looks like that, where this slope is same, but the x-axis intercept has decreased. So let us see among the option which was correct. The first option is it moves the entire curve to the right. No, the curve does not move entirely to the right. Moves entirely to the right means, suppose initially the curves look like this, then it will look something like this. No, the curve is not looking like that. It moves the entire curve to the left, that would look something like this. This is also not happening. This second option is also wrong. It has no effect on the slope. Now look at the slope. Obviously we can see from here that the slope has increased. Why? Because the slope is Km by Vmax. So your m has been increased after the inhibitor has been added. So obviously the slope will increase. So the statement is wrong that there is no effect on the slope. Again, this is wrong. And the final option is it changes the x-intercept. Yes, the Km value changes and thus the x-axis intercept value also changes. So the only correct option was option D, that the 4 number statement was the true statement. Okay. Now comes the last, I think this is the last question probably. So it states, a classical uncompetitive inhibitor is a compound that binds. Out of these 4 options you have to choose. So till now we were talking about competitive and non-competitive inhibition. So let me make it very clear again. So we did have 3: competitive, non-competitive and uncompetitive. So for competitive one, we already know the inhibitor forms EI complex only. Fine. For non-competitive ones, the inhibitor can form both EI and ESI. But the uncompetitive one, it only binds after the substrate is already binded to the enzyme. That means it only binds to the ES complex, forming an ternary complex ESI, which is inactive. So if we write down the mechanism for the reaction for uncompetitive, it looks something like this. This is the normal one. The non-competitive inhibitor will only and only interact with enzyme substrate complex by forming ESI, which is an inactive species and not lead to any kind of product formation. So this is the basic difference in the reaction mechanism for competitive, non-competitive and uncompetitive. Be very clear with that the competitive inhibitor binds with the enzyme only. Non-competitive one binds with both enzyme and the enzyme substrate complex, but the uncompetitive one only and only binds with the enzyme substrate complex, and obviously in a reversible manner, and ESI is in an inactive species. So according to this particular question, our correct option was option B. Okay, there are other questions. Okay, let us see what this question is saying. It is stating, potassium cyanide is a poison which combines with cytochrome A3 to prevent binding of oxygen to the enzyme without altering the Km of the reaction with respect to reduced cytochrome C. Which type of inhibition does this represent? So the very important point here is the Km is not being altered. Why this is very important? The main thing that you do need to remember again, that how does the plots for competitive, non-competitive and uncompetitive inhibitors look, the Lineweaver plot, how does this change for this 3 inhibition process? For competitive, after adding the inhibitor, the curves look like something like this, 1 by V versus 1 by S, and there is a change of Km value. This was for competitive inhibition. From non-competitive inhibition, how does the curve look like? I have just explained. Again, 1 by V versus 1 by S. Your curve looks something like this after adding the inhibitor. That the Km value does not change, but the Vmax value does change and the slopes gets changed. And what is the case of uncompetitive? In case of uncompetitive one, if this was the original one, 1 by V versus 1 by S, then after adding the inhibitor, you will get a parallel line. That means the slope remains same, that is the ratio of Km by Vmax remains same, but individually both Vmax and Km, both the value decreases, both the value changes, but the ratio remains same, giving you the same slope, and it shifts to the left. Okay. So for this one, once you know the Lineweaver plots, here also you can say that after adding the inhibitor, there is a change in Michaelis-Menten constant. One is Km, another is Km prime. So if you do remember, and you have to remember this 3 type of curve for Lineweaver plot, then you know only in the case of non-competitive inhibition we get the same Km values. And as the question stated already, that the Km remains unaltered, that means the mechanism of the inhibition has to be non-competitive inhibition. Okay. Okay. So this was question. So it already become 8 by discussing week 4. That's not a problem. One second. Let us do for another 5 minutes and then I will stop the session. But let us continue for another 5 minutes. So these are some questions for your week 5. So some question will be done easily. This is also related to enzyme substrate complex formation and inhibition. So the very first question states, which among the following can act as a choline esterase inhibitor? So we already know, if you look at the lecture slide, it is a memory based question, that the insecticides that are generally used are choline esterase inhibitor. Choline esterase is an enzyme. Esterase, it is the type of some kind of esterase, already from the name you can understand. It inhibits the action, insecticides inhibits the action of choline esterases. Okay. Okay. This statement says, we have already, I think, discussed similar things. Okay. Identify the correct statement regarding the allosteric regulation of enzyme. Just in the previous week's one of the questions, we discussed that what is the allosteric inhibitor. It is basically something which can, it is a small molecule generally that binds some other site of the enzyme rather than the catalytic site, and then it induces some change in the enzyme molecule which can then further be activated or inactivated. So basically the correct statement, let me come to the first statement. A small molecule, so if this is our, one second. So if this is our enzyme, then allosteric inhibitors or allosteric regulations in case of enzyme, they can bind to the enzyme molecules, induce some change in the enzyme which can further activate, regulate or increase the activity of the enzyme in some cases, or inactivate the enzymes in some cases as well. This is the very thing that is stated in the first statement. So our option 1 was correct. The second statement says the small molecule generally binds close to the active site of the enzyme. Sorry. It does not matter. Suppose your enzyme looks like this. This is your catalytic site. For allosteric inhibitors, the small molecules can bind other sides of the, rather at a far distance than the active sites as well. So the second statement, that they generally bind close to the active site, is not necessarily always correct. And the third statement is the regulation generally arises from the conformational change in the enzyme when the ligand is bound to it. Obviously, I just stated that once the small molecule does bind, once the small molecule does bind, if somebody, I would please request to mute yourself. Anyway, so once it binds to the enzyme, it does leads to a conformational change in the enzyme which further leads to more activity or less activity for the enzyme. So yes, our third statement is correct. And the fourth one is hemoglobin and myoglobin show equal extent of allosteric effect in presence of oxygen. No, this statement is not correct because hemoglobin has 4 subunit molecule. So in that case, whenever one oxygen molecule binds to one of the subunits, it does change the enzyme in such a way that the other subunits becomes more active to take oxygen molecules. So it increases the activity. Once one oxygen attaches, it increases the propensity of other subunits to attach with oxygen molecules. Okay. But in case of myoglobin, this will not happen because myoglobin is a single unit protein. It's not a 4 subunits, so it only binds with one oxygen species. So there is no case of allosteric effect in case of myoglobin. So our option 4 was also incorrect. So the only options that were correct for question 2 is 1 and 3, that is our option C was correct. Okay, so fine, we will end today's session here up to this and discuss the other question in the next session as we do. Let me stop the recording.